engineering from the Institute of Technology Tallaght, Dublin, and Nanjing University of Technology, China in 2012. He's now pursuing a Master's by Research in the Radio Frequency Technology Centre in the Institute of Technology Tallaght, Dublin. He won the President's Research Award Scholarship Scheme in 2012 at the Institute of Technology Tallaght. His research interest is in low power consumption RF front-end circuit design.
Hello everyone, my name is Kansheng. I'm from the Institute of Technology Tallaght, and I'm supervised by Brian Keel from Limerick. I'm also co-supervised by Professor Max Aman in DIT Antenna and High Frequency Research Group. You may not familiar with what a low-noise amplifier design is, but I believe most of us have seen those two icons. Your receive sensitivity is too low that you can't get access to the Wi-Fi signal. The second one is probably the disaster. Your battery is dying. You can't use your mobile phone. So what can we do to improve this situation in the RF area of the receiver to be specific? So the power efficiency of a low noise amplifier, similar to Class A power amplifier, we use the RF power divided by the DC power of the low noise amplifier. Consider we have a minus 100 dBm signal coming in, which is 10 to the power of minus 10 milliwatts. And if we have two different antennas, the one is 5 volts and 50 milliamp, the second one is 2 volts and 10 milliamp, the efficiency would be calculated as 10 to the power of minus 9 or 10%, which is quite low. But consider this, if we reduce the current from 50 amp to 10 milliamp, we deliberately improve the power efficiency by a factor of 12. The research question becomes, how can we design a low power consumption low noise amplifier? The RF receiver front end would be, the block diagram is shown as figure 1. The antenna and the low noise amplifier would normally be designed as a 50 ohm impedance to get the maximum power transferred, and the filtering and matching components in the middle would introduce actually the path loss for the low noise amplifier. And my proposed design is here, if we could get rid of the input matching circuits and also using a voltage regulator to examine the lowest possible power consumption for the low noise amplifier, we could solve those two icons, maybe never see them again. A low noise amplifier design would involve those 6 hexagons trade-off. Obviously, the noise figure and the gain would be the most important thing here to consider, and also the power consumption and other 3 things would be taken into consideration in this project. And also in the RF circuit, normally a 2-part network is used to describe these components. Particularly, S parameters are used to describe the low noise amplifier. For example, the S11 is used to describe the input reflection coefficient, and S22 is the output reflection coefficient. As you could consider, it's the lower the value, the better. So the receiver blocks becomes the 2-part network shown here. The antenna, the matching circuit, and the low noise amplifier. Particularly for the low noise amplifier, it has the source reflection coefficient and the load reflection coefficient. Normally, the source reflection coefficient is contribute to the noise figure, while the load reflection coefficient contributes to the gain. Therefore, there exists a gamma opt at the input sides for a lowest minimum power, lowest noise figure for the low noise amplifier. And if we could bypassing the matching circuits, the gamma opt is designed to directly match the antenna. We could get rid of the input matching circuit. The research method would break down from a standard matching, input matching and output matching for both 50 ohms. And then the power efficiency part of the project is going to the voltage regulator is used to examine the lowest possible power consumption level for the low noise amplifier using an E-type transistor. Then if after the lowest possible power is located, a digital tunable capacitor is used to replace the input matching circuit. The algorithm from the software is designed to tune the gamma opt or gamma s, which depends on which way you're looking at the signal. The gamma opt would be located by this digital tunable capacitor sweep in the zone of interest. And then once we got the value for gamma opt, the non-trivial antenna is designed. And it is designed in software and also a practical work. For the first stage, standard matching, as you can see from the Smith chart, basically the idea is to get into the center of the Smith chart to give you a better result. As you can see, we aim for the low noise consumption, the low power consumption for a low noise amplifier. That way we sacrifice a little bit for S22, which is considered the GAN part. And also for the current examination, number of currents is running through the low noise amplifier design. It's too complex for too many figures for S11 and S22, but basically the result shows that 8, 9, or 10 milliamp would be enough for the E-type transistor. And just to improve a little bit for the S22, the output inductance value changes from 1.5 nanohenry to 2.7 nanohenry is examined. I'm not going to show too detailed for this one, but at 1.8 milliamp, the blue line shows a better result here. So for a standard matching, the results is shown here. We aimed at 2 volts and 9 milliamp for the E-type, and the noise figure is 0.8. The gain is 12.5. That's the sacrifice for the gain. And also 1 dB compression point is minus 6.3, which is considered the linearity part. For the second stage, a digital tunable capacitor is used to replace the input, and the simulation result is shown as this. I have also a little video. The software increases the value of the series capacitor, and as you can see, the greater value it is, it gets through to the center of the Smith chart, which gives us the best noise figure result. And also the simulation here shows a different way of looking, because the S41 test shown in the figure is looking from the source part, and the gamma opt here in the simulation is looking backwards. That's why it's not in the center of the Smith chart. Here, as we know in the gamma opt, the inverted F antenna is designed with the help of Max, and here the particular impedance for the port here, feed port here for the antenna is 33 minus 25 j ohms at 2.4 GHz. The result and conclusion for this project has then improved the DTC matching circuits. Also, the source port techniques is proved to work, and also the direct antenna transistor interface is sufficient for the low noise amplifier, and also the lowest possible current consumption for the E-type transistor is used to prove that it gives a good noise figure. And also we save the energy, and also the DTC board actually it's a low cost solution for source code techniques. All the results is tested, as you can see, is an RF analog chamber in Tallaght. And thank you very much.
It's just history, is it? So what you're saying is that there's a lot to be gained by optimizing the impedance of the antenna.
But the thing is, for a standard matching, everything is designed, considered separately. You could design an antenna for PPO, and any